So yeah, I'm wearing the shirt so you can tell who is from Facebook, who is from Broadcom. We're going to talk about a topic that is kind of borderline between networking and storage, a collaboration we did with Mark. Many of the kind of keynote addresses had always the topic of whether Moore's law is dead or slowing down, anything like that. And Mark at Broadcom is making sure that for networking, Moore's law is alive and well. So we're trying to capture that benefit going into our data center network design. The fact that we're still on a kind of linear clip per Moore's law every couple of years, getting 2x the bandwidth. Mark will provide a background on the collaboration.
Yeah, and I wanted to acknowledge C.Y. Chang. He couldn't be here today, but his work was indispensable. His contribution was indispensable to this work.
Awesome. So from our perspective, coming from the Facebook cloud operator context, what we have, as you know, is more than 2 billion users, so a set of services that are very high scale, very successful in their own right, constraining the fact that they have to have continuous operation, and we don't want to be limited to incremental improvements in that. So whenever we look at new things that are disruptive, how do I deploy things that are more valuable than what I was doing last year? The question becomes, okay, I have twice the bandwidth, I want to deploy new things. How do I make sure that I can predict, optimize, and not break what was running before? So that's a context for the idea of simulating what we're about to propose. If there is a word that it will make you friends within Facebook, as you know, is the word disaggregation. That word has no negative connotations. Every association is positive. And the sub-bullets are why, because the disaggregation has CapEx, OpEx, and operational advantages that are very, very compelling, because it lets you deploy things in arbitrary ratios, not having to know exactly what the optimal deployment is. From the network point of view, the network is what enables that disaggregation. Disaggregation for us enables, in particular for Flash, to remote something that was directly attached to you. So we have to be there to enable that, to make sure that we do not break it. So that's what we wanted to set out and simulate. If we're about to disaggregate Flash with reasonable scale, number one, will it work? Number two, will it break anything else? In the context of doing that, we're going to be looking at stuff like latency at the average and at the tail. It's a very kind of controversial topic, always talking about latency. There are people that believe that it doesn't matter, there are people that believe it does. So we wanted to quantify all that. And in particular, we wanted to layer everything over TCP, and we can touch on why we wanted to do that, to make sure that we're friendly to the rest of the network.
Okay, so the method that we can use in order to see whether the system is fit for purpose and also to optimize it among many different options is network simulation. And by system, what I mean is everything that's in the data center. So, the different components, the protocol stacks, the applications that are being used, are these things working together to provide the overall performance that's needed? And network simulation is predicting the overall performance of a system by looking at the dynamic interaction of all the different components. And that includes processing and queuing delay in many different places in the overall system. These simulations were done using NS2 and NS3 frameworks. The benefits of network simulation are primarily in the ability to experiment widely and also in the evaluation of those results. So you can very easily put together different combinations of systems and model them in a way that is easier than constructing the actual systems, both the physical construction of those systems, the procurement of the systems, and actually writing fully functional and working software that does those things. This also can be done while the devices and systems are under development. Many combinations can be tested in parallel. For the evaluation results, you have full observability of any key things in addition to the actual metrics that will be used to judge the results. And the ability to control the simulations, go back and do sensitivity analyses, aids in the interpretation of the results. The limits of network simulation are both in the accuracy and scale that can be achieved in the simulation itself. For accuracy, there are you can model what you know. So if you know that a component will behave a certain way or that it has a certain performance aspect, those can be modeled directly. If there are unpublished algorithms, those can't be modeled. Also, you have to use judgment, right? You have to choose which are the components that are going to be modeled and how to abstract them. From a scale perspective, I mean, we're trying to draw conclusions about an entire data center or actually a group of data centers working together and what their performance will be. But that entire system can't be modeled. So we have to draw conclusions from something smaller than that. But the thing is, all models are wrong, but some models are useful. So we have to actually just make the right decisions about abstraction, just like you always do. The model that is used in order to draw conclusions here, so this describes both the physical topology and protocol stacks as well as the application characteristics. The physical topology here is both 2- and 3-tier simulations using a class topology that are interconnected with Broadcom Tomahawk 3 switches using the Broadcom Tomahawk 3 model. And that has network level oversubscription at the first tier. The model size can be up to 640 servers in addition to the storage head nodes. And a few other key aspects here are that you have persistent TCP connections between long-term communication peers within the network that are talking to each other at the application level. And that this is using the actual transport stacks that are under consideration with the production settings that would be used for those. The applications also are accurately modeled. So these are both the front-end workload, meaning web workload, based on captured statistics of the actual application, and generic storage clients for both read and write, accessing the storage service through the head nodes.
So still on this slide, this is the physical topology that we decided to simulate. The learning started the moment it's starting asking the questions, what is it that we want to simulate? And I'll show you a couple of examples. Here we said it has to include a TCP as an endpoint, as a form of end-to-end kind of behavior that includes some behavior that resembles the application. And we have the actual transport that we either use in production or considering for production. We also model multi-host NICs that you may have seen when you look at Yosemite Type 1 platforms. So there is an extra layer of switching that happens at the NIC. So all that stuff was captured in the physical topology. Then we went into how to model the upcoming storage queuing model. And then we learned a lot by formulating this and starting to simulate it. The workloads are very different between the background traffic, which is what exists today and we don't want to break, and the new emerging workload in the form of storage. Storage is a few connections going very, very fast because I/O tends to be very bursty. So you'll see color-coded the kind of the purple and the bluish type of head node to client associations, where the cardinality is very low. It's tens or maybe 20 clients per head node, unlike the other tiers that have cardinalities of maybe 100,000 servers talking to another 20,000 in the next year and so on. So these are few connections that go very, very fast. Whenever I run simulations, I always start with, you can do your Poissons, you can do your normal distributions. I always like to try bursty on off because it's very stressful, whether you're a car driving in a highway or any other process that wants to go fast and then it stops for good. So we did bursty on off, and the choice that we have to make is whenever that queue grows, whether we let it grow to infinity or whether we truncate it, like it happens in real life. All queues have a finite size in real life. So we decided to let it grow to infinity to capture the essence of what we're simulating, because if you truncate it, it's no longer bursty on off. The other assumption that we wanted to make is whenever we cannot model something perfectly, we want to be pessimistic. And pessimistic from the point of view of analyzing the contribution of the network to latency is to assume that everything else is infinitely fast. So we model a head node that has an infinitely fast CPU with an infinitely fast media. Other talks like way later on discuss what are the kind of noisy neighbor effects in the media itself. Here we're assuming that the media is perfect and we want to analyze the contribution of the network. So here what you show is the physical topology and the client on the left and the head node on the right, and that's what we call the storage, either read or write workload that we impose on the network. This is superimposed on a landscape which resembles a 3-tier architecture, a little bit more complex than that. So if you go back to the, I don't know, late 90s to the venerable 3-tier architecture, you have a presentation layer, you have some kind of a stateful application, and you have databases and caches. That's what we capture in what you see as T1, T2, T3. So the model that we decided to create is essentially, there is a user at the end of the line on an iPhone or on a browser or whatever it is, going through a number of stages of load balancers that we call T0s. We skip them, we do not model, and we end up in a web-facing type of server. We call that a T1, and we model that. The behavior of that tier is such that a query coming in has a finite probability of being responded right away with a blue response that you see there, or propagating into a concatenated request for another query to the next tier, which again has another finite probability of coming back right away, and then the chain returns all the way to the server, or it goes all the way to a database tier. And our concern is, because of this concatenation of requests, what is the impact of an aggressive workload on top of that? Will this survive, or will this be impacted by storage? In addition to that, and this has temporal statistics and spatial statistics, how many web-facing servers are matched to a cache tier and so on, so we capture that by measuring. So we have distributions for that, and we capture the packet size distributions and the statistics of what's the chance that a query is replied right away versus propagate to the next layer. All that game is a game of metadata. The objects themselves come from a separate object storage, and we capture the bandwidth of that going into the network as well. We call all this the query traffic, and the previous slide we call it either the read or write traffic.
Okay, so we also have to know how to evaluate the simulations, see the suitability of the system. Simulations produce a lot of data, and some of the data items, such as throughput and packet drops, are areas that somebody might typically want to look at, looking at it from a performance standpoint. But really, you need to see what is it that you're going to use in order to draw your conclusions. And at the end, those are really the flow completion time of the 3 primary types of flows: the user queries, storage reads, and storage writes. And for each of those metrics, we're looking at both the median and also tail statistics, specifically P99.9, with most of the emphasis on the tail. These metrics are collected at the target application, and that means at the good put that is desired.
So we had a number of questions here, a few examples of the things that we wanted to predict. For example, what's the ratio between clients and head nodes that we want to deploy based on constraints that the network may impose, not just on a back-to-back configuration? Is there any benefit of sprinkling all the head nodes across different racks versus having a heavily flash-oriented head node with lots of storage behind it? As an input to the simulation, we did some analysis on the connection between the SSD density and the bandwidth that it wants into the network. When do we need to 100 gig links, and where? The typical historical deployment of faster speeds is always from the interior of the network to the edge, with the idea that unless you can go kind of single flow at the fastest bandwidth, there is no point in going faster at the edge. So all the adoption of newer speeds has historically been from the interior out. Oversubscription of the spines, what's a reasonable number, does it matter? Short packet, it's harder and harder when you design switches to do 64-byte forwarding. You don't want to kill yourself over that performance if it doesn't matter. So we wanted to answer that question. Do we have elephant flows? Is that a problem? Do we have to break them somehow? And the Tomahawk 3 buffer architecture is brand new, completely different than Tomahawk. So we wanted to say, okay, there is no operational experience yet. What does it do to a network that has this level of complexity of 2 different distinct workloads?
Okay, so getting into the actual evaluation of simulations, so we have 6 different workloads that are described here on this slide progressively. So starting over on the left, this is a 2-stage or 2-tier Clos network, which is the base model. And so we're looking at when we just put in the queries by themselves, the user queries to the front-end application, what are the statistics that we see for that? And establish that as a baseline. A second baseline is when there are only storage read requests and that the reads themselves are achieving the entire intensity that we want from the storage application. what tail latency do we see for those? And so at 50% of the head node link, we're seeing 5 milliseconds of read completion time. And so we'll anchor the goal that's what we want to see as we actually layer additional things, in addition to the interaction of the write and read traffic as well as query traffic in the overall system. Then running just the write traffic on its own, see that the write intensity is the same. So the bottleneck there is really the link to the head node, and that's also happening at the 50%. Specifically, in the case of the reads, they're going to directly affect the application performance. In the case of the writes, we don't need to bound a specific delay for them, but just see that it's not exploding at the expected intensity. Then combining read and write application together, where half of the intensity is write and half is read, now the RCT is being affected. In fact, it's up 20x versus the original baseline, right, where the reads were on their own with the same total amount of intensity. So we'll just record that and come back to that at a later point. But looking at how the other types of traffic relate to each other. So if we just have reads and queries, the queries are not being negatively affected by the reads or vice versa. And when we put the reads, the writes, and the queries together, we essentially just see the same interference between the reads and the writes that we saw when reads and writes were together. So no additional effects.
Who thinks that this slide is hard to read? Okay, so let me set you straight. Each one of these tables over here is a simulation run of roughly a day or a couple of days. So just the fact that you can condense a couple of days worth of execution into a single table is magic. And after a while, you get used to that and what you're looking at. I'm looking at the P50, I'm looking at the P99. And if I had to take you back to this slide, what we're looking at is the statistics as observed at what we thought, you look at the top of the FIFO D2C to on-off request. So it includes everything, one read request, going TCP all the way over NBD to the head node, coming back, and the request being correlated with responses. That is what the table is showing you. One thing that was very interesting that happened in the course of doing the simulations is that we started smoothing the intensity from the high side. We see why was running this, and we said, why don't you start at 80% load? Namely, this the sum of all the requests would occupy 80% of the head node link. And at that point in time, we discovered that simulation did not converge. Like the read completion time was proportional to execution time. So you let it run for 2 days and they have a value. 4 days, double the value or something like that. At that point in time, we went to some of our TCP experts and said, well, the network is unstable. And the guy said, there's no way. TCP is there to make sure the network is stable. And he was right. What we had was an unstable system because that queue that we decided to keep of infinite size would grow to infinity, but the query completion time, the victim traffic was happy, was not affected at all. So we learned that even if we break the flash disaggregation traffic by putting too much intensity, it will not affect the other traffic. And that's the value, for example, of having a transport like TCP that will make the network stable. So that's something that we learned right away by chance, by moving from the high side. So that was the base model. We said, well, this is broken, let's break it a little bit more, because now we want to go to a network that is more real. So we took the base model and we said, by now, let's make it real by having 3 stages. So we have the rack switches, the fabric switches, and the spine switches, just like we have in our data centers. Let's oversubscribe the spines. So we went 133-to-1 oversubscription. And we have region-wide traffic, which is cross data centers. Sometimes the caches are not in the same data center as the databases. So they have to cross what you saw, the FA, as you were showing the FA fabric. So we added another 150 microseconds of latency between those 2 tiers. And on top of that, we threw in a multi-host NIC. So that is what we call the extended model. And instead of fixing, we're trying to make it more realistic. So we rerun this one. I hope that the picture on the left is clear because I think I made it a little bit bigger. What we saw is that by and large, the RTT did not affect the flash traffic, and it affected a little bit The multi-host did, and it affected a little bit the query completion time at the tail, at the P99.9, not at the average. That is because a small fraction of the requests make it all the way to the databases. Some of them are taken care of at the web tier or the cache. So we said, okay, what we call the queue workload, which is the previous query traffic, is happy even after we went to a much more constrained network. Then we go to the third bubble, what happens to the read workload? When we look at our flash, the main latency that we care is the tail latency of the reads. The writes are the spoiler, but the figure of merit is the reads. We saw it was a little bit higher. We had some drops in the multi-host NIC because of rate adaptation. But the very elegant part that happened, we're not sure why, for all the simulations, is that the knee of the curve of the completion times happens at the same intensity, and that's a function of the intensity of the head node link. It's a percentage of the head node link. And it tends to be around 40 to 50% of that. So if you have a 100 gig NIC over there, you'd better not operate it much higher than 50% goodput, because that's when you start going into the nonlinear part of the curve. Then we put the workload, what we call W, just writes into flash by itself. We don't care about the tail latency of that in terms of absolute value, but we care about the knee of the curve, and we saw that the knee was at the same spot. Everything is good. We put the three of them together, and it's broken again, because the read completion time got twice as worse, going to 623 milliseconds. Mark described what the metrics were. The calibration for the metrics is very simple. We do not want to dominate the latency. We looked at the media, and we say if the worst case when you're doing garbage collection in the media is a P99.9 of 3 to 5 milliseconds. If we're single digit low milliseconds, we're comparable, we're not going to dominate, we're uncorrelated to that one. If we're 600 milliseconds, we break the entire solution. So this is where the simulations took us, and this was the beginning of the engineering that says, now can you use the simulation to fix it? And by the way, when this was very broken at 623, query completion times were completely unaffected. Kind of saying, even if flash hurts itself, it will not hurt the other traffic. And that was a major realization that we had after simulating. Ideas?
Okay, and just to follow up on that, right? So when you have network and server and application contribution, and the storage contribution are each have a P99.9 that are roughly the same. It means that the P99.9 of the sum of those two metrics will be very close to either one of them, because they're uncorrelated. They're both very far out on their tail. Okay. So here this is one particular path to rein in the RCT from that starting point of 600 milliseconds. The first step here is to do actually two different changes applied at the same time here. One is really like orchestration. It's placing more restrictions on what clients can access a particular server, storage server, in order to make sure that there is a more even distribution of load among the different servers within the system. And second is to round robin the requests to the TCP connections. So because each individual TCP connection can only achieve a certain amount of bandwidth, Ariel showed in the NBD picture earlier that there are several TCP connections that can be accessed by a single network block device. And so this is using those in a round robin fashion rather than binding them to a particular request. When those two things are applied, the RCT tail went down by a factor of 100 to 6 milliseconds. And then, let's not be satisfied with that. We can do one more thing and get it down to 3 milliseconds, which is to actually pace the requests at the client side. So this is essentially saying that the client is reading data, and that is going to go, if you look at the path that the data is going to take, it's going to have to get out of the storage device, go up to the top of rack from the head node to its top of rack, go through the network, finally get to the multi-host NIC that is requesting it, and from there go through a PCIe interface, which is the most severe bottleneck of the entire path. All the other points, they may be more multiplexed, but they are all higher bandwidth. And we know that in this particular case, that the the read is fully using that bandwidth, right? If we're trying to get this there as soon as possible. So if we just say that we're going to space out the different parts of the read according to how fast the PCIe could accept it, that's not going to actually delay the completion at all, but it will make the congestion that is injected into the network less. And so again, you can see that that reduces the RTT from 6 to 3 milliseconds.
The round robin is a very important one. This is not a simulation in isolation. You've seen the Tioga Pass machines and the lightnings we have there, so we have a setup like this in the lab. So the first thing that we did is to test round robin in NVD, and we saw a regression because of the diminishing of your ability to batch requests. So this is the age-old tension between network efficiency and server efficiency. Whenever you want to be efficient at the server, you're hurting the network and vice versa. The factor of, 300 or something ridiculous like that, or 200, essentially says, be friendly to the network. It's more important than being efficient at the head node. So it's a call to action for our people to go to a round robin type of mode. The other one that we tested is what happens if instead of going round robin, I'll give you a 200 gig head node link. Here the knee of the curve moved up from roughly 48 to 50 gigabit per second to 64, and the read completion time was down to 8 milliseconds from like 600. And then we combined that with client-based requests, the idea that Mark described before, brought it down again to 6 milliseconds. This emphasized the idea that it's not that there are good ideas and bad ideas that are incredibly impactful. It means that the first good idea that you apply gets most of the benefit, and the second one gets diminishing returns. Here we took out round robin, put 200 gig, and you get that benefit. We could have run 200 gig and round robin and everything else, and bring it further below to the low single-digit millisecond.
Okay. Facebook's application the base application is known to have small packet sizes compared to many different applications. This was the purpose of their 2016 presentation in SIGCOM of inside the social networks data center network to make sure that really the overall ecosystem is designing for the use cases that Facebook needs. And so a natural question here is, we have a packet size distribution that includes a lot of small metadata type packets. If we have switches and other devices in the network that are not operating at a 64-byte throughput, but are internally oversubscribed, is that going to affect the overall network performance or the overall application performance? And so the simulation allows us to answer that question directly, because this is real applications. These are simulations that can be used in order to draw conclusions about how to actually use the protocol stacks, modify protocol stacks. And so it's quite solid results. So what you can see here are the very worst top of rack switches, and then all of the spine switches that are in the simulation. And the red bars are the average amount of backlog that the actual Tomahawk 3 model is experiencing, compared to a purely line rate switch that is doing 100% of all ports at 64 bytes. And the green bars are the 99th percentile. So what you can see is that the backlog is actually contained to less than 2 packets, and that really there is not even any measurable difference in performance between this and a line rate switch in the application.
So putting all together, we went back.
Time check. We just have maybe 1 or 2 minutes left.
Done. We went back and said what was our intuition going into the simulations that we do learn, and maybe half of them we confirmed the intuition, half of them we realized that we were wrong. The one that we want to point out is the importance of 200 gig as a way of solving the headland link bottleneck, as a call to action to enable an I/O subsystem, say OCP 3.0 with by 4 Gen 4 PCIe for the multi-host NICs as an example of what we need there, or by 16 Gen 4 for the head nodes. The other one that we're discussing with Mark is the idea that in the spirit of open source and community, the accuracy of what we model is based on the contribution that people make. And maybe Mark, you want to touch on that, on the NS3 contributions?
Yeah. We started the simulations here in NS2, which is actually an older model. It is world-class, but it's older than NS3. We started there because it actually has a more complete set of models than what is already in NS3. And so what I'd really, but NS3 is definitely a technically superior solution. So what I'd suggest from a community standpoint is if more people can both adopt NS3, file bugs, upstream your code, which really has often not been done in the case of NS2, that means that the overall community is going to be benefiting from a more capable ecosystem. And also, if there are people who are providing parts of the solution, such as the TCP stack itself, if there's a way for those to get directly put into the framework, that will benefit everybody who is trying to draw conclusions from this.
Thanks again.
Thank you.